All right, so I think my job is to kind of fire you up and say, we're going to solve all the problems of the world, and we're going to do it not by talking to one another. Here's the challenge. The challenge is that when I'm presented with a problem, who do I talk to? I talk to other surgeons, I talk to perfusionists, a real stretch. I even go talk to the cardiologist. But the bottom line is, we're fundamentally similar, even with the cardiologists. Our backgrounds are the same, we're all trained in the same way, and we tend to think of how we solve problems by boundaries which have been imposed on us as we've kind of gone through medical school and training. There's a great quote, actually, I should have put it in here, from Steve Jobs at Stanford address, is dogma. Dogma is the flawed thinking that somebody else basically has passed down the line to you. And ultimately, I think the people who are going to make big leaps forward have to be able to challenge the dogma. So all of a sudden here, I'm a Scottish guy. We got North Sea oil, but I end up in Houston. And I end up basically in an area that has got incredible engineering talent. And you also have it here in New Orleans around the oil and gas business. And we also have incredible engineering talent, not just in the oil and gas business, but in the aerospace industry. And so what I'm going to do is try to persuade you that there's a lot of value in looking, and one of the themes we've used is the other guy's toolkit. How do we see into the toolkit of people who approach like problems but with none of the preconceived constraints and dogma that have been posed on us as we work basically through the various different branches of medicine. And so part of this concept then is we started this thing called Pumps and Pipes. We started about 9 years ago now, so we're coming up on our 10th year anniversary. I've given this in many different places, both in the United States and around the world. This is not just a Houston thing. Oil and gas and aerospace and medicine is a kind of a Houston thing. But I think if you were in LA, you'd be thinking about simulation. How do you use the talented people who are around you to help approach some of the challenges really that we all have? And this is actually from Bill Klein. Bill Klein was a guy who I started Pumps and Pipes with, and Bill Klein runs Exxon Mobil Upstream Research. They used to be the biggest corporation in the world until Apple took that spot, but nevertheless, this is a research guy. And the research upstream means from the platform all the way down the hole. That's where all the technology is. When I found that Bill has $1 billion a year research budget and runs a cohort of 900 PhDs in Buffalo Speedway, 4 or 5 miles from the medical center, this is a guy that I need to get to know. And he has now taken this concept, and this has been presented at the Society of Petroleum Engineers, it's presented in the Middle East, of looking into the medical toolkit, and we'll show you some examples of this, of how they can use it in the oil and gas business, and increasingly pushing into NASA. So let's talk about the like technologies, and this concept of the answers to my problems probably don't need to be invented. They're probably already out there. And the problem is that we live in little silos of how we function on a daily basis, and there are very few platforms where we can talk to people who do similar but fundamentally different, or that tackle fundamentally different challenges. So let's talk about some of these things, and I'll show you examples of this. Anatomy of pumps and pipes. Well, it's the heart and the vascular system for us. I use a word, you'll see it again and again in this presentation, is the word flow assurance. That's what the petroleum engineers told me, that they are in the flow assurance business. I said, no, you're not. I'm in the flow assurance business. That's what we do on a daily basis. Their job basically is to deliver volume flow from subsea to onshore with all the different challenges that face, when you're running a cardiovascular circuit or you're putting in bypasses. Blood and oil has the same rheology. They're both non-Newtonian fluids. They behave in the same way as they move through these various different sets of tubes. Blood and oil get infected. How many of you knew that you get infections in pipelines? When you hear about a pipeline coming apart, it's because it's infected. So microbial-induced pipeline corrosion is $1 billion a year problem. It's one of the things that they're very interested in, how we help them. And I'll talk a little bit more about that. We deal with stent fractures when you put them in the lower extremities. We deal with valve fractures. And these are probably the world's experts, basically, in metallurgy and understanding, how you have flow occurring continuously and how you pump continuously and how you interrogate these things and try to intervene before the problems actually arise. And they also use a variety of different imaging techniques. They also have this ability to take a drill, they call it directional drilling, and they can put it on a target, and they can have from the surface, and they can hit a target 20 by 20 feet, 5 miles offshore, and 10,000 feet down without turning on an X-ray machine and being able to see what they're hitting. I think those of us who are in the endovascular world can probably learn something from them and how to do this. And you can see basically the variety of different things from nanotechnology to, and we'll talk about fracking. They actually referred to at one of our meetings as building an underground vascular system. And how basically do you create these networks, subterranean networks that allows oil and gas actually to flow. And so once again, basically, I think we're all happen to be basically in this flow assurance business. Now, let me give you an example of how this can work. And this is one of the reasons that those of us in the vascular world are certainly aware of these kind of opportunities. There's a thing called the Greenfield filter. It really was called the Kimray Greenfield filter. And that's because Laser Greenfield was a chairman of surgery up at Michigan. But when he was a young attending, he was working in trauma service, and he had a young man came in with a motor vehicle accident. He basically went through a series of operations, and he died 4 days later from a massive pulmonary embolism. And he happened to be talking to his next-door neighbor. His name was Garmin Kimmel. He was an oil services guy and a pipeline engineer. And he told the story about how this guy got a pulmonary embolism. And Kimmel says, well, you should put a filter in the tube coming out of the legs. He says, that doesn't exist. There's no such thing. And they said, you mean put a sieve in there? I said, I can't put a sieve in a flowing pipeline. The whole damn sieve just blocks up. That's just stupid. You've got to exploit the fact that there's laminar flow. Center line is basically the maximal flow. You need a conical shaped filter, so you trap things and flow goes around the side. And that led to the concept of the development of almost every filter that's out there that exists to this day. And that really basically were the two guys who kind of came together, the surgeon the clinician who identified a problem, the engineer who had the solution for the problem, and then the other part of this was a guy called John Abley. And John Abley was one of the founders of Boston Scientific. Boston Scientific, Cook, Guidant, all of these things started in somebody's garage, and now are multi-billion-dollar corporations. And what Abley said was that great invention is always a metaphor. You look at a problem, you try to connect it with other areas which have nothing to do with that problem that you're working on and come up with a solution. And the business guy is the one who can take that. There are a lot of great ideas. I guarantee you for every invention that's out there, there's 20 people who said, well, I thought about that. And they probably did. But the genius is thinking about it and then delivering it in a form that can be delivered to the marketplace. And one is not any good, frankly, basically, without the other. And so these are just some examples of what you're looking at. Top left is a pig. Not the little pink things with the wiggly tails, but this is a whole science which exists in the oil and gas business by how they interrogate pipelines. They have hundreds of miles of pipes, and they have robot pigs that are actually delivered simply by the flow pushing these things along, and they interrogate it. And they can interrogate it, and they can, with ultrasound, show whether there's defects basically occurring in the metal. And they have pigs that can actually take samples of what is blocking off the pipeline. And then they have therapeutic pigs where they can actually build solvents, package it in there, and actually treat and dissolve the atherosclerosis that's building up on the inside of that pipeline. And so this is an incredibly important part of how they manage and they maintain pipelines. And what you're looking at in the bottom left are robots. The problem is that for us, of course, those pipelines are not all 18 inches in diameter for the next 200 miles. They change in configuration all the time. And so what you're starting to see is these little robots which are being created, which can expand and flex dependent upon the diameter of the pipeline. And these are all kind of tracked basically with GPS. Now, when you look at directional drilling, now, if you go for a liver biopsy, the radiologist will be looking at the target, and he's got a straight needle, he's got to stick straight in there. Can't bend those things around the hepatic arteries and the hepatic veins. You got to basically have a straight shot. And yet these guys can actually, using directional drilling and differential drilling, by opening these baffles on the end of these drills, these things will deflect in a variety of different directions. And they have to seal the junctions. When you make a hole in the ground, it's not just a hole that all the oil comes bubbling up from. It has to be cased from top to bottom. So it is lined by steel from top to bottom with multiple junctions, and those junctions have to be positioned without being able to see them, and they have to be able to seal. So here's the challenge. You're going to hear a lot of great surgeons here this afternoon. They're not being held to the same standard that these engineers are being held to. 99.99% assurity that when you join that tube onto the aorta, that it ain't going to bleed. When you talk to one of these engineers and they say, well, how do you connect these things together? We tell them, and they say, how do you know it's not going to leak? I said, well, actually, you take the clamps off, and you kind of go, oh my gosh, put the clamps back on, toss in a few more stitches. They are not allowed to do that. They got to be able to pressure test these things, and they got to be able to guarantee that there's going to be no leak, and they can't even see it. So this is being done remotely. So again, other examples of things that we can actually learn. And when you look at these so-called multilateral lateral wells, main bore, side branches. What you're looking at here is an example of one of these side branches. Looks very like, endografts, which we still can't basically necessarily make it seal. And so they've got to be in a situation where it's first time, every time. Can't just put it in there, see if the seal exists, and then toss in a few extra stitches if it doesn't. They're held to much higher standards. And this is going to dovetail into my talk that we're going to do tomorrow, in that for some reason or other, in surgery, bleeding is considered part of what we do. I would submit to you that bleeding is never good and is representative of bad disease, bad technology, or bad surgery. And that we need to move to a situation where zero tolerance for bleeding when we join these things is going to be the norm. It's going to be a challenge. It's going to be a long way. But this idea that bleeding is part and parcel of what we do should be less acceptable, basically, than it currently is. So joining, testing, monitoring, and intervening prophylactically is part, really, what they do. Because if this happens to your aorta, you don't make the national news. If it happens in some pipeline in the middle of Yellowstone Park, it is all over the world of how evil you happen to be. And I would submit to you that happens in every operating room in this country, often on a daily basis, and should probably not be acceptable. So let's look at so we started off really with the oil and gas folks, and then we were approached by NASA because NASA's congressional mandate is they push their technology out. You can almost get free technology for them. But they don't really do it very well. They kind of expect you to go there. But you can get technology from NASA remarkably cheaply because it's one of their missions by which they get funded. So navigation, directional drilling, we've talked about navigating a catheter. If you think about what they're doing subterranean, it's exactly the same as trajectory control from a rocket, inside NASA. Very similar control system. How do they join the tubes together? Well, maybe NASA can learn a little bit from the oil and gas guys because they've not been doing so well in joining all these different structures together. What they do, though, at NASA is train people extraordinarily well. They do a systems failure analysis probably better than anybody else. And so there are multiple things above and beyond just the hardware that we can probably actually learn from them. Robotics is increasingly going to encroach on our operating rooms and our hospitals. And I'd submit to you that NASA really are some of the amongst the world leaders in how to manage those things. So what happened then was NASA came along and they joined us and really have taken this consortium really to a whole different level. Okay, so this is one of these things that resonates in Texas, probably resonate just as well in Louisiana. Why does the quarterback throw a spiral? Why are we in awe when you see, oh my gosh, look at how he threw that spiral right in the end zone and the receiver caught it? Why is the bullet spiraled down through a rifle barrel? Because it's a way of moving a structure with less frictional fluid losses than you get basically if the thing is wobbling all over the place. You know what that thing is in the bottom right-hand corner? That is a dynamic MR looking at the left ventricular ejection into the ascending aorta. So the quarterback didn't invent the spiral, and the quarterback didn't invent the rifle. God invented the fact that the left ventricle contracts and rotates, and it spins blood up into the ascending aorta. And that propagates actually up the carotids and actually down the descending aorta. And there are certain companies now who are actually building these spiral baffles inside grafts to try and maintain this and see whether we can improve patency. Remains to be determined whether that's the case. And look what pipeline engineers have been doing really for the past 30 years. They build spiral baffles. They've known about this inside the pipelines, particularly when they're trying to move structures around bends. Again, things that are there in biology that have already been identified in another industry. And we're pretty late in actually trying to emulate this inside the cardiovascular world. Now let's talk a little bit about directional drilling. I don't think we need the music. What we're going to see here really is different ways of creating a hole through a structure. This hole through the structure happens to be a blood vessel in this particular situation. And what you're going to see in the bottom is a very similar situation where they're using directional drilling. They can actually bend these catheters by creating a baffle which moves on the outside of that drill and moves it in very specific directions. And so they can hit these targets without having to go straight down into it. And what that means is they can go from one well, they can go way basically into a variety of different structures. They can hit areas that otherwise were not economic to actually produce. And then what they do is they can extend these horizontally, so you get these long producing wells inside the structure. And then what they do is they case them. So the entire structure has to be lined with quarter-inch steel from top to bottom. And all of that has to be delivered through that little rig thing that sits up on the surface up to 4 or 5 miles away, and then they have to be joined. And then what happens is you come down in here, they bring in what's called a fracking gun. And this is the big controversial area. These are shaped charges that are put down in there. And what that does is it creates this underground vascular system that we're talking about. And so one of the things we're very interested in is, can you frack muscle? Can you deliver a fracking catheter down into an occluded blood vessel and create these perforations, perhaps seed them with stem cells, and actually use this to try and recreate an underground vascular system and emulate something that's going on, in the oil and gas world. So I think it's very important to have an open mind. When you look at, so as we're now using intravascular ultrasound, basically, or we're using a variety of different catheter-based methods of interrogating the blood vessel, what you're starting to see is very similar patterns to what is seen in well logging. Again, they can't see the way we can see. They use a variety of different methods of interpreting resistivity, for example, in rocks, by passing electrical currents through it to see what the resistance is of the rocks. That's how they identify which rock formations they're going through. Likewise, they flow mud. They flow basically fluid down into the area they're drilling through, and they analyze the particles that are coming back. Again, these are things that have not really been built into our catheter-type technologies as we've got at the moment. Sealing technologies. When you build one of these multilateral wells, if you hit water, then you'll have a very expensive water pipe that's coming up out of the ground. And when you're talking about, anywhere between $50 and $100 million to drill one well, you don't want to be producing water. And so on the outside of these are water sensors. What these basically do is, as soon as they sense water, these are packers which will automatically swell up and fill that space and seal it off. And there's a lot of places, in the cardiovascular world where we're trying to fill spaces and fill voids from intracranial arteriovenous malformations. And that's one of the projects going on at Texas A&M with so-called swellable elastomers built onto catheters, to this void that occurs around endografts when we actually implant it. We really want to fill that space, and it's what drives the reinterventions. And in fact, one of the new devices is a so-called Nelix device, in which is two covered stents, in which there are these bags that are put on either side to try and to cover these space. And as I say, some of this has now been pushed into intracranial aneurysms and will continue to be looked at. You can also, this is out of the Baker Hughes lab. Baker Hughes is one of the big oil services companies, and they make swellable foams that can be delivered through small catheters that will again swell up massively and then harden and fill these voids. And again, potential uses in the aortic aneurysm and left atrial appendage. So it's not all things that we can learn from them. One of the things we did was we do this behind-the-scenes tours where we bring in engineers, and we'll take them behind the scenes in the heart center. And they all love watching. For lay people and engineers, they want to see open heart surgery. They want to see the heart stop, and they want to see patients going on the pump. But what really impressed them is the imaging and the quality of imaging that we've got. And these are dynamic MR scans that we produce really on a daily basis. You can see the papillary muscles, you can see the valves opening and closing, you can see ventricular function, and we can see flow basically up in the aorta. And if you look in here, what you're going to see is an aortic dissection. And you can see how dynamic that flap is, moving backwards and forwards. And that's an area of research interest really for us. So they were very impressed with us. Again, same thing I showed you earlier. What you're looking at here is an MRI scan and showing this type B aortic dissection. And what's important about MR is the cardiovascular imaging modality of the future. Not only does it show you the anatomy, but it's all quantitative. We can calculate these velocity flows, we can calculate resistance, etc. And it can show us, as you can see here, what those flow patterns and flow lines actually happen to be. Now, we'd show those pictures all over the world, and they go, great pictures, great numbers. BS. How do you know that you're actually measuring something and it actually is correct? And so this is a project that came from working with ExxonMobil. We told them their problem, and they built what we call, runs our cardiovascular hemodynamics investigative laboratory. And what you're looking at here is the first product from Pumps and Pipes. You can dial in the left ventricular pressure volume curves. We can input that into a circuit, and we can test structures. But we wanted to put it in an MRI scanner. We could do that. We couldn't get it without any metal in it. And so they built this from non-ferromagnetic. They designed it from top to bottom. These are ExxonMobil engineers. And they built what's called the heartbeat simulator. This is probably one of the most sophisticated systems in the world. You can see the hard part basically is getting ExxonMobil and Methodist brand on this thing. When it went through the ExxonMobil lawyers, and the explanation was it was going to be, it's called a heartbeat simulator. They thought ExxonMobil were building an artificial heart, and that we were actually planning to implant this. So that kind of slowed it down a little bit. But what this allows us to do is to move the pumping system outside the 3 Gauss line, which is on the floor, and we can create these pressure volume curves, and we can actually look at structures. And here's a model of an aortic dissection. This is a pig aorta. Create a model that is then put back into the circuit. We can pressurize it. This is intravascular ultrasound. You can see the flap is developing. We can watch these things propagate, and we can emulate and measure exactly what we had in a clinical situation. And this really has allowed us to validate the use of dynamic MR as the means by which we evaluate all the aortic dissections now. And this is kind of when you put this model into the MR, these are the path lines. It's showing us the flow real time. And as I say, this is all quantitative, and it allows us to model it. Now we got companies coming. This is actually one of the Gore devices. Basically, they're using their hybrid graft, trying to model what happens in the flow, because this is the best way really of doing this. Now, one of the things, this is what ExxonMobil did, is we thought they were being very magnanimous, but what they did was they came along with a patient. So we're always interested in building our patient basis, and so they said, we want to bring a patient for you. Well, they turned up with this thing. And this thing is a model of the bottom end of a well bore, all made up in plastic. Now, they wanted to pump ungodly amounts of fluid through this thing, which kind of got us a little alarmed, because this was going inside a medical MRI scanner. And what this allowed us to do is to look at how flow occurred through those shape charges that they blew. Because turbulence equals loss of is resistance, loss of energy is loss of production. And so they completely remodeled how they use these shape charges, and this is being tested the first time. The medical MRI scanner had really been used to model how flow was occurring into the bottom of a well bore. And this was actually published in ExxonMobil Shareholder Magazine, talking about melding energy and medical breakthroughs. And, you know, but it doesn't stop there. Now we're in this transcatheter valve world. There's several talks that you're going to hear about it, and you can see how these are now actually being modeled. Again, and we'll show you how this was done. These are 3D printed aortic roots. And in them, there is both the calcium, the white stuff is the calcium, and the more compliant stuff is actually the aortic valve itself. And what was important was, again, validating the in vivo clinical observations with what we were creating with these models. We hooked it up to that pump, which is the physiology. We now created the anatomy. And you can see that on echo, these valve Doppler signals were almost basically were very, very similar to one another. And so it validated this model, which we can now use basically to test about why does a valve not seat? Why do you get paravalvular leaks? How can we actually change these things without having to do it in a patient? And this is what a core valve looks like when it's deployed inside a calcified modeled valve. And again, when you put it back in the MRI scanner, it lets you completely model the flow patterns that are occurring in the bottom of the aorta. All righty, so we'll keep moving on, I trust. There we go. And so the reason I push MRI is because I think it's so valuable in being in one stop, being able to show you these huge anatomical fields. It can show you supraortic trunks, the carotids, the descending aorta, and the heart, and it lets you calculate what is going on basically with these flow patterns inside this. I threw this in here for you, Joe, because I wanted to talk a little bit about simulation. Simulation is incredibly utilized at NASA. They're probably amongst the most experienced simulated people in the world. I got to fly basically the space capsule and dock it with the International Space Station. And they have to do that first time, every time. You can't basically be screwing that thing up and ramming it. And so simulation is something that is used in the space world, but it's also used in the oil and gas world. Again, they simulate every well that is going to be drilled before they actually do it, and we'll show you a little bit about this. And so this is this sonar system, and here's your noble leader basically playing with this when he's in Houston.
All right, so there's the pressure coming down. You see it flattening out, losing the pulse pressure, so we're emptying the heart. I'm at 4 liters a minute, not completely emptying it, but it's getting better.
So I think medical simulation remains in its infancy. It needs a lot of validation to actually show, because what we really want to be able to do is we want to put a surgeon on a simulator. But that needs to be validated to say that this is real and that we can qualify him or disqualify him based upon the performance in the simulator. Credentialing in hospitals is one of these highly politic and controversial things. To have some sort of objective way of doing it, it's got to be validated first before we can even introduce something like that. But nevertheless, it is certainly coming. And so I'm going to let this video play for a minute. This is now moving on to robotics and how this can potentially apply.
Well, the Methodist folks approached us with the goal to use some of the technology that we're proving out both on the ground and in space for having the robot help humans perform tasks. In this case, medical tasks, with both ultrasound and injections as part of the ultrasound procedure. And Robot's doing really well going after those.
After training lots of colleagues and physicians, I thought I would like to give a shot to train Robin. I would say that within an hour I trained him more than with other students I'm working for a week. So I think he's learning really fast.
I think he's talking about the cardiologists when he say that, probably not the surgeons. But NASA's going to Mars. That's a 2-year space flight. If you're in orbit around the Earth, you can be back down on the ground within about 5 or 6 hours. If you go to the moon, they can get you back in 2 days. If you go to Mars, you're not coming back. And the distances are so huge that these has to be completely self-contained. You can't talk an astronaut through a procedure. They have to have all this self-contained on the mission craft. And a lot of this, and the only diagnostic tool that they carry is an ultrasound. Can't put a CT scanner or an MR because it's too heavy to actually launch. So this is how they train astronauts even to use ultrasound is fascinating for us in terms of how they color code all the different knobs and buttons that are on there to make it a little bit easier for them to actually understand. It's one of the things that we're interested in. And this is actually Tom Mashburn. He's had flown at least 2 or 3 flights actually, and he's a physician, was actually learning to use ultrasound. One of the things that got a lot of press last year was really us imaging, and this is what we call the Advanced Imaging and Navigation Laboratory at Methodist Hospital. This is not for patients, this is just for R&D. Luca was an Italian astronaut who was out on a spacewalk when he felt something behind his head in this particular spacesuit. And what happened was that he had a leak. In that spacesuit, there is a pump and a series of pipes. It needs to keep them warm. And what happened was that leaked, and it leaked inside his spacesuit. And he got to the point that this bubble of water was in his face. He couldn't breathe. He couldn't see. And he lost communication basically with the Johnson Space Center. And so he was rescued really by his fellow astronaut, but almost died because of the amount of fluid that was in there. And it happened because there was bacterial infection in the pump, which backed up the pump, which resulted in this tubing rupturing inside the spacesuit. And so again, even this is about pumps and pipes and trying to figure out how do they do prophylactic maintenance. They don't, when these spacesuits go up, they stay there until there's a problem with them. You may be wearing, Dr. Bath, you may be wearing my spacesuit that I wore today. Now, when you're out there, there's lots of stuff goes on inside that spacesuit because you're not coming in to pee. You got to basically hang out there. So you got to be real good friends with the guys who's going to be wearing your spacesuit tomorrow because it ain't coming back down to be cleansed. And so they're up there for long periods of time, and you got to be able to figure out why this happened and what happened to that tubing system. And we're doing all that imaging. This is another example of an exoskeleton, and you've heard a lot about this in the news, basically, but this is actually being tested over at the VA, and it's something that was developed by NASA. They actually were doing it to try and have the astronauts wear this, because an astronaut has to spend about 1.5 to 2 hours a day exercising because they lose bone and muscle mass, and so they put this exoskeleton on to try and create active resistance so they wouldn't have to exercise all the time. And then they found that they could actually augment the function, and this is being used really for folks who are paraplegic. So I'm going to close actually and give you a video that kind of pulls a lot of this together, and we'll show you a lot of these different projects that have spun out of this association with NASA and association with oil and gas. This is the famous JFK moon speech. My office looks straight into Rice Stadium. And you can see in the background, it says Rice Stadium. And what Kennedy said there was, but why, some say, the moon? Why choose this as our goal? They may as well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? And in his own handwriting in there, before this, he penciled in, why does Rice play Texas? Sure, if you're a Rice fan, so let's climb the highest mountain. We chose to go to the moon in this decade, not because it'll be easy, because it'll be hard, because the goal will serve to organize and measure the best of our energies and skills, because that challenge basically will unite us. And so that basically was created in Rice Stadium, and you're going to hear some of his words in the following video created for NASA that we introduced pumps and pipes with a couple of years ago. No, let me bring it back.
And this city, and this state, and this region will share greatly in this growth. What was once the furthest outpost on the old frontier of the West will be the furthest outpost on the new frontier of science and space. But this city of Houston, this state of Texas, this country of the United States was not built by those who waited and rested and wished to look behind them. Because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all people.
So Pumps and Pipes happens in Houston the first week in December. It's broadcast in nearly 2,500 different places around the world now that pick up this webcast. It's also got a very important part in STEM education, and HISD has picked it up, and we have a whole group focusing on how do we stimulate high school kids to focus on STEM education. This is the website. We can tell you what's coming, and we thank you again for the opportunity to talk to you today. I hope you're stimulated to look and think differently in the couple of days ahead. Thank you.